Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is how to increase efficiency in NFC and RFID systems with magnetic shielding. Our speaker is Antonio Alcaria. He will hold a presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. So now I will hand over to our speaker and I wish you an exciting presentation.
So I hope everyone can see me now. Welcome everyone. Today we're going to talk about how to increase your designs in NFCRFID systems with the using of magnetic shielding. I'm Antonio Alcarria. I'm part of the EMC Shielding and Thermal Management Solutions team in Würth Elektronik, and I hope you find this topic interesting. First agenda, we're going to talk about what an NFC RFID system is, what are the problems we are going to talk about, and we're going to define and let's try to find out solutions for. Why is this happening? So what's the origin of these kind of problems? Which solution we propose? And it's one, we will say later, flexible solution, one of the more easiest one, we will say. Then we are going to show some results about measuring the behavior of these solutions and how can we deal with these problems in a real world approach. At the end, we will have some additional information and references. So for this, this is on what we are based this information, and also if you need more, where you can find it. So first of all, what are NFC RFID systems? We can find them all around us. Nowadays, if I think everyone is paying now on the mall or in any shop, you can pay with your phone, you can pay with the watch. You use it also to storage some of the cards, the loyalty cards. For example, if you have to a sports store, things like this, and you have the typical loyalty programs, these ones can be stored also on phones, also info scanning. I have seen also this kind of things in the nature to identify the different kind of plants, also in animals. So at the end, this is a technology that has a lot of uses today, and is extending and increasing and growing every year and every year. It is basically composed. We have an antenna, an attack, or two different antennas, which can identify each other and offer some information to the user, for example, of a phone or even with a card to enter security systems through the doors and so on. So what's the problem? The problem comes when any kind of these antennas that we are designing, if when the designer point of view, are close to any kind of conductive surface. So every part that is conductive, like metallic housings, batteries, ground planes, and many more, can be affecting the performance of the antenna. We are going to see how much and why. So this is a very difficult problem to deal with sometimes because it decreases the performance at the end, the the optimization of the system, and also the distance of communication, the power transferred, and so on. All these kind of problems, then therefore they make not possible a good communication or the intended communication from the designer for an NFC or RFID system. Why is this happening? The main responsible for this, together with the conductive surface that is close to the system, are the eddy currents. About this, I'm not going to dig in a lot in the technical aspects of the eddy currents. We are going to see the more practical part about how they are affecting NFC RFID systems. Here we have a transmitter and here we have a receiver. Typical NFC RFID system that we can see. For example, this could be an NFC antenna from the phone, and you can think this is a tag, or this is from a security door system, and this is your card to enter to your company. So this antenna is creating an electromagnetic field that is uniform all around it. And we can see that here we have a conductive surface. This conductive surface is able to absorb part of this electromagnetic field that is created by transmitter, and some currents are created on the surface of this conductive surface, or this part, this metallic part. These currents are created and are creating an opposite field. This one that here is called secondary field. This secondary field is interacting with the first one, that is the intended one, and is mismatching the intended design for this antenna. We're going to see later how this creates the mismatch. Also in the additional information, you can get more information and more simulations and so on about these problems. So it is possible to calculate the power loss created by eddy currents with a conductive surface close to our system. It comes, or it starts with the magnetic flux formula, with the magnetic field and the surface. At the end, we have this derivative. I'm not going to go through all the mathematics, but we have this derivative, and when we integrate this part, we get this final formula, which gives us the total power loss created by this eddy current when we place a conductive surface close to an antenna. It depends, as we can see here, this is the magnetic field, and it depends directly on, here we have frequency, but talking about the conductive surface, it involves the width of this conductive surface, or the thickness, you could say, in this case, because we will talk, if we talk width, length, and widthness and thickness, this is the thickness, and the resistivity of the material that is composing the conductive surface. With this, it is possible to calculate the power loss created by any conductive surface close to an antenna. Which solution are we exploring here? We have these two kinds of solution that basically act in a similar way. We have the flexible sintered ferrite sheet and the flexible absorber sheet created for this application in specific. I'm going to talk later about why it's created in the next slide for this purpose. So about the composition, first one here on the left, this is the WE FSFS. And basically, it's an easy placing material that is composed by a ferrite sheet, the same ferrite you can find on ferrite cores for cables and so on. And this ferrite sheet has some pre-cuts that make them bendable and more flexible than a normal ferrite surface. This one on the right is a bit different because it's like a host matrix that is a rubber or a polymer, and embedded on this host matrix, we have some iron powder. And by playing with the geometry, the size of the iron powder flakes that are embedded on this material, and also the density and the orientation, we can achieve higher, or let's say better performance or lower performance in terms of interacting with electromagnetic fields. What's important to know about these two materials? First of all, they're really easy to place. You don't need to do any redesign in your device because you can just use it with adhesive tape. They are also non-conductive. This one, of course, the ferrite is conductive, but it has some PET tape, and also adhesive is isolating in order to avoid any kind of shortcut in your design. For this one is made with this special rubber on purpose to be non-conductive. Important to know about one thing I would like to say here also is the permeability. The permeability is a value that give us how the material behaves against electromagnetic fields or interacts with electromagnetic fields. It has two components, the mu prime and mu 2 prime. Mu prime give us an idea of the ability of reflecting of this material, reflecting the magnetic field, and the mu 2 prime represents the ability of the material to absorb the magnetic field. By playing with these two values, we can create materials that are designed to be used on these situations. So in this situation for NFCRFID, we will want to have a high mu prime reflecting ability, remember, and low mu 2 prime or absorbing ability. Why? Because we want the material to reflect. If we place the material in the middle, we will see later, to reflect the electromagnetic field and prevent it to reach the conductive surface. On the other hand, we don't want the material to have a high mu 2 prime, because then it will absorb the magnetic field and it will create an effect of not the same as the conductive surface, but it will create losses also on the transmission. Here we have a simulation. Sorry, not a simulation. This is an experimental result. Simulations I will show at the end a graph for people that are more interested in getting more info. This is our experimental results measuring with an NFC antenna and placing a metal on top. So this is the signal of the antenna measured. S11 parameter means measuring with one antenna, NFC near field proof, measuring the signal that is received. Or you can measure directly with in this case, with the PCB. You connect the network analyzer to your PCB, this PCB that is the antenna, and you are measuring the transmission power or the ability to transmit of this antenna in the same way you will do with a normal antenna. So we can see that for the antenna standalone with any kind of interaction, we have the peak here. So this is the antenna transmitting. This is all power that is reflected, and here is the transmitted power of the antenna. So the antenna is transmitting in this spectrum here. If you remember about NFCRFID technology, it works normally at 13.56 megahertz for the communication systems. So here is where the antenna is tuned around that frequency. In this way, the tags or the receivers or any kind, they are tuned to be listen at this frequency also. This way they can communicate to each other. So we have the measurement for the standalone antenna. Now we introduce a metal plate, and we can see that from 13.56 or around, we are going to more than 15 megahertz in the communication frequency. Also, the power transmitted is much lower. We are going from here that is, I will say 18, 19 dBs until 13 or something like that. So it is lowering the power transmitted by the antenna, and also is mismatching the antenna and messing with the tuning that we designed for the antenna. In this way, if the antenna is transmitting at this frequency, the listeners, the receivers, are not going to receive anything because they are waiting for this frequency and not for a shift in this frequency or in frequency of this kind. When we introduce different kind of shields, the shields are this material in different thicknesses. we can see that as we are increasing the thickness of the material, it's the same material, different thicknesses, we are taking back to the original shape the behavior of the antenna. I would note, or something to keep in mind, is that if we also go over the limits and we select just the thickest material with the highest permeability, we can create the opposite effect. Instead of taking it to the original antenna behavior, we can take it to the lower frequencies, and we can create a frequency shift to the lower frequencies. So we need to be careful also on this. We need to select the material that is going to be working properly for our application. This is the parameter I was talking before. This is the permeability, or it's called relative permeability, and as I said, it has two components: mu prime representing the reflection ability of the material of the magnetic field, and mu 2 prime representing the absorption or absorbing capacity or ability of the material. As we can see here, this one is also a FSFS of 150 of mu prime. And as we can see, as explained before, we want to have a very low or almost zero or zero of mu 2 prime, no absorption, in order to not create losses to the system. We want all the electromagnetic, the magnetic field to be reflected and not to create any kind of losses. This is part of the problem that the conductive surface is creating. Normally for these materials, we have a resistivity that is higher than 1 gigaohms. It depends on the material. For example, for the FAS, it's common to have until 10 gigaohms, so it's more than enough. How you place these materials? You place them between the conductive surface or the affecting part and the antenna. In this way, we're creating two effects. We're preventing this electromagnetic field to reach the conductive surface that could be problematic, and at the same time, we are redirecting all the field that was getting lost in the part that is below the antenna. We're redirecting it upwards. So in this case, we are increasing or improving the total power that is transmitted to the receiver. So it has a double effect that is that have a lot of benefits for our device. This is the measurement setup that we use to measure or to explain the performance of this material. We wanted to check in a real world application kind of measurement to show how this material behaves. We are using an EM scanner. This EM scanner is composed by a matrix of small near field proofs. Each one of these squares is a near field proof. What the software does is to compilate and to handle all this data for the different near field proofs and creates a matrix of all of them inside the program. You can see levels like using it. You can see it in level graphs like you use it in a spectrum analyzer, or you can use it creating heat maps that is quite useful, as we will see later. You connect it to a spectrum analyzer with the different adapters and so on. What we are using for the NFC transmitter is we took directly a commercial one. In this case, you can see here, it's from Texas Instruments, and it's basically just an NFC transmitter. So we have two different positions. One is the antenna standalone on top of the EM scan. We select only for measurement this part. The one good thing or one benefit of having this near field proof matrix is that you can select only the area that you want to measure and to avoid any kind of external disturbances from other areas. Even in your own PCB, we could select this one. We'll see. So we have first, we have the NFC system, only standalone to measure the reference signal. Then we are including a battery, a cell battery. So it's just a normal one that you can find off the market. In this, with this approach, we want to simulate, for example, the using of a cell phone for paying, or the using of any kind of device which has a battery close to the NFC antenna. you need to take in account that nowadays all electronics are getting smaller and smaller. So, and at the same time, they are working in higher frequencies. So they are working very close together. And in this regard, we are having the batteries very close to the antennas and to the different systems like the RF stages and so on. So here we place the battery on top of the antenna, and then we place WE FSFS between the battery and the antenna. And now we're going to see the results. So for the first measurement that you please remember it was the standalone antenna, we are measuring communication frequency of 13.56, so it's well tuned, it's well designed, and the maximum power transmitted is 76.7 dBs at this frequency. So we can see the tuning is quite nice, the power is quite nice. So we can also assume that the transmitted power by this system is quite good. It has a very high level. There are lower levels, like for example for watches and so on. If you measure it so many times, the level is much lower. So this one has a lot of power. Here you can see the heat map of this area only. This you can see here the shape of the antenna quite easily. Now we measure the second part. In the second part, we are including on top on the antenna. We are measuring on the other side. Please remember. So we are not interfering directly between the near field proofs and the antenna. The near field proofs are here on the bottom. Then we have the antenna, and then on top we have the battery. So in this case, we are trying to demonstrate that the battery or a conductive surface is absorbing part of the signal. If we see before, we had 76.7, now we have a peak of 59.9. So it's decreasing a lot the transmitted power. Also, you can see the heat map. The third part is where we include the FSFS. When we include the FSFS in the middle, not only we are recovering the initial or the original transmitted power, that we are also increasing it. For the initial one, we had 76.7 dBs, and now with the FSFS in between the battery or the conductive surface and the antenna, we are reaching 84.1 dBs. So it's preventing the problem from the battery, and at the same time is increasing the initial power that the antenna was able to transmit. Why? Because it's redirecting, as we explained before, it's redirecting the field that was lost in this side, because we don't need to have any kind of communication on this side, and it's redirecting it to the part where we want to have, or to the direction that we have, where we want to have the signal. So as we can see, the improvement is quite nice. One thing to remark here is that we didn't measure any kind of frequency shift with the battery. This depends also on the metallic surface. One thing that is clear is that always a metallic surface is going to cause losses. But here with the battery, we didn't measure any frequency shift. As we will see later with other setups, we measured frequency shifts, quite big ones, as I showed on the graph before. So in conclusions, materials with high reflections and low losses are able to redirect the magnetic flux. We are demonstrating this with this graph and this measurement. Eddy currents that are close to the that are created on the surface of the conductive surface are reduced when we introduce these materials, these kind of materials, because the inductance of the transmitter is increased. So when we're introducing these kind of materials, increasing the permeability of the antenna, we are also increasing the inductance of this transmitter, and that's why a big part of why we are reducing the effect of the eddy currents. So the magnetic shielding is able to increase the inductance and to concentrate the magnetic field. Magnetic shielding is able also not only to recover the original transferred power, but also to increase it because of the concentration or redirection of the magnetic field. So at the end, the magnetic fielding prevents the high power energy consumption due to the power loss. So because if we need some kind of power source, well, of course we need a power source for the NFC antenna. But if we need to reach a certain power level, we will need to have more power supplied to the antenna if we are having losses caused by different conductive surface. When we use this kind of materials, we're preventing this and we are able to be more efficient also in energy consumption point of view. We prevent the mismatching between transmitter and receiver. This is what I talk about the frequency shift. This is demonstrated also for the other setup that is showed here with this frequency shift from the original working frequency. And finally, we avoid a high temperature on the device derivative for the eddy currents effect. If we think about the eddy currents effect, this is how the kitchens, the cooking systems on the kitchens work, with the eddy currents effect. So it's something that can heat up the conductive surface. And it's something that we prevent by using this kind of materials. So about some additional information, we published part of this presentation I did on the symposium of the IEEE, something extended for people who want to have more information and with more details, also with Smith charts and equivalent circuits of the antennas and a much deeper analysis, more mathematical and more technical. You can find it in this paper, Design Approach for High Efficiency NFC Systems with Magnetic Shielding Materials, that we published later in the MC Europe. And some results from this paper are these ones. We were analyzing, we created by ourselves instead of using this commercial one. We created a standard NFC antenna that you can find on phones or any kind of tag. That was this one. We were measuring this antenna. We were simulating it also with the ANSYS software. So we created the simulation models and we were measuring the experimental part at the same time. Here you can check, for example, the different measurements to see if the simulations were right and were correct or not, and the matching level with experimental results, and they were matching quite good. And here we were measuring, this is one example of one of the measurements we did. We saw the difference in inductance when we're including a metal on the antenna and things like this. So we can see here the normal antenna has this level of inductance, and when we were including the metal on the antenna, close to the antenna, we're reducing this inductance. This reduction in inductance is messing with the matching of the antenna that we designed. Remember that for the matching, you need to calculate the inductance and the capacitance to include your capacitor and your inductor to tune the antenna. Once we place close to the antenna a metallic surface, we are messing with this matching. This is part of the problematic issue of this conductive surface. So this is all included in the second paper, and if you need more information, we'll be glad to provide it. Or also, if you want a more technological deep presentation, please feel free to request it, and also to include your comments on the poll that will be sent to you later. I hope you like this small presentation, and if you have any questions, please feel free to ask.
Thank you very much, Antonio, for your interesting presentation. Like you already said, we will turn our attention now to your questions and wait a little while until some questions have come in. Well, let's have a look. Okay, so we can start with the first one. Is there any other influence from the material of the NFC antenna besides the permeability?
So besides the permeability, this is something that you can find, for example, in the application notes that we have for the FAS. when you want to select, also please let me go to the graph where I saw the different thicknesses. There are 2 points that are going to have an influence on the final performance or on the tuning on the antenna when we are introducing this kind of materials. One is the permeability. We need to select a material that with a permeability that fits for our application. As I said, we don't want to have too much or too less, and this is the same with the thickness. So we need to have a kind of a balance. In this kind of balance, for example, if we have our device and we have very few space to include any kind of additional solution or something like that, we can select a material with very high permeability and with a thickness that is very low, like very thin material. If we have space enough, we can do the opposite. We can select a material with lower permeability values, but thicker material. So it's a kind of a balance. If you remember here in the graph of the power loss, we had that the influence were coming from the resistivity and the thickness of the material. So we can see it in the same way, in a similar way, but in this case will be the thickness of the material and the permeability. So we need to keep in mind the thickness of the material and permeability.
Okay. So there's another question about the material. Are there more materials which can be used on such applications?
So in this case, the most common ones are these two materials. There are also, it depends on the application which one you want to use. The difference between them is for the FSFS, the ferrites, it's possible to reach higher values of permeability. For the FAES, it's more complicated because remember that it's a host matrix made of polymer with embedded particles, but it's a more flexible material. It can be cut easily even with scissors, can be easily customized in any shape, and it normally has the UL rating or the flammability test passed. So for these ones, it's normally not possible to have this UL test or this flammability test passed because of the PET foils that need to be included in order to increase the isolation against or the conductivity, the electrical isolation of the part.
Okay. So I think we will finish now this presentation. If there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is high frequency three-phase PFC solutions for high power charging stations from our partner STMicroelectronics. So hope to see you there and enjoy our digital days. Goodbye.